What I would like to do today is I would like to focus in on one particular aspect of this conversion route, and that is on the hydrogenation of levulinic acid to valerolactone and also beyond valerolactone, as I will show you at the end of the. So we wanted to see what kind of conditions our catalyst could withstand and when it would break down, when it would deactivate. As also said in one of the previous talks, we expose our catalyst to liquid phase conditions in polar media under high temperature and high pressure, which are basically conditions that our catalysts don't like very much, and these are very demanding conditions, and we want to know what they could stand, what they not can stand, and how to deal with this deactivation. Okay, so when we set about with this study, we first synthesized a series of supportive ruthenium catalysts where we basically varied the acidity of the support. We took niobia, titania, and 2 zeolites as support for the catalyst. And what I will try to do in this talk is I will try to systematically list the synthesis procedure that we use, because this is quite important and it has a big influence on the outcome of the reaction. So we started with a standard hydrogenation method using this precursor listed here, and in this particular synthesis we include both a calcination and a reduction step for this for the catalyst synthesis. We obtained ruthenium particle sizes of 3 to 3.5 nanometers in all 4 cases, which basically allowed us to make a fair comparison between the different catalysts. We test our catalyst in levulinic acid hydrogenation in a bench autoclave. We do our reactions at 200 degrees C and at 40 bars of hydrogen. And we do not only vary the support, but we also vary the solvent. So our standard reactions are run in dioxane, which is basically we consider mild conditions, allow us to assess activity and selectivity of the catalyst. And then we move to harsher conditions. We do our reactions in neat levulinic acid, and we do our reactions in a solvent called 2-ethylhexanoic acid. And the latter is quite a nice solvent, because basically here we really we really put our catalyst under severe conditions and when it will break down. So the goal of these studies is not to really to do a reaction on a larger scale in this solvent, but to really see what kind of modes of deactivation we can encounter for our catalyst. Okay, these were our first results, and I would like to focus today on this bar here for ruthenium and titania, and later in the talk I would like to focus on the zeolite supported catalyst. So what we depict here are basically product distributions after a given amount of time, and what you can see is that for ruthenium and titania we get nice and clean conversion to valerolactone. So this has been seen very often in the literature, and basically ruthenium and titania has become one of the benchmark catalysts for actually doing this reaction. So well in line in literature, and what we would like to know is how stable is this catalyst and what can it do under more forcing conditions. The second thing that we noted from our initial screening here are these red bars, which basically are pentanoic acid, which shows that these zeolite-supported ruthenium catalysts can do the direct conversion of levulinic acid to pentanoic acid in one step and in one reaction. And what I will show you later is that we can actually make these bars a lot bigger, and that we can quite selectively go all the way to pentanoic acid if we design our catalyst right. So what we did then is we exposed our ruthenium titania catalyst to more forcing conditions. We ran our reactions under in neat levulinic acid and in ethylhexanoic acid. This ethylhexanoic acid is quite a nice mimic of levulinic acid. It has the same pKa as levulinic acid, but it doesn't get consumed. So we basically run our reactions under a constant acid concentration, really forcing conditions for the catalyst, and see what happens. We then characterize our spent catalyst quite extensively and noted that ruthenium and titania is actually quite stable. What I show you here first is the conversion in ethylhexanoic acid, and also under these conditions we get nice and clean conversion to valerolactone, and we don't form any byproducts, or maybe 0.1% of MTHF, but that's it. The reaction is slower than in dioxane, of course, because the substrate has to compete with the solvent for absorption on the catalyst surface, but still the catalyst maintains and actually can do the job and go to full conversion. If we then look at the spent catalyst, what we see is that the catalyst is rather stable. So regardless of the solvent, if we do it in dioxane or if we do it in ethylhexanoic acid, we see no leaching of the ruthenium to the solution. The leaching is less than 2% of the original metal intake. We see very little coke formation. We see very limited sintering of the ruthenium nanoparticles, and we also see that by XRD that the titania stays intact. So ruthenium and titania seems to be quite a robust catalyst. And I put the word seems there because later in the talk I will show you that this is not always the case, and that also ruthenium and titania can actually deactivate under quite mild conditions, I have to say. But that is for later in the talk. Having established these titania-supported catalysts as quite promising, we further explored this system and we made a variety of different titania-supported catalysts, and we also made some bimetallic catalysts. So if you think about bimetallic catalysts, then they are actually relatively little explored in the levulinic acid to gamma valerolactone reaction. There are two prominent examples from the Jurassic group where they show that ruthenium-rhenium catalysts have an improved stability against poisoning by traces of mineral acid, and ruthenium-tin shows improved long-term stability with respect to the monometallic catalyst. But in both cases, the improved stability actually comes at the expense of a bit of activity. So the catalysts are less active but more stable. Well, we had our postdoc Sankar in the lab who's very good at making very well-defined random nanoalloys of gold palladium and ruthenium palladium, and we wanted to use these also in the hydrogenation of levulinic acid. And they turned out to be quite exceptional catalysts for this reaction. These catalysts are made in a quite specific way. This is called a modified impregnation method. This method was developed at Cardiff University by the group of Graham Hutchins, also together with Sankar. And basically, this method, what it allows is it allows control over the size of gold palladium nanoparticles, and it allows control over the composition of gold palladium particles. So how does it do that? Basically, there are two important steps in this synthesis procedure. It's a wet impregnation, but it's a modified wet impregnation. And the modification is in the fact that basically you do the wet impregnation in the presence of half a molar of HCl. So you do the modification in the presence of an excess of chloride anions. And this excess of chloride anions ensures that you have very intimate mixing between the gold and the palladium, and that you have very good control over both the size and the composition of the nanoparticles that you make. The second important step of the modified impregnation method is that we omit the calcination step. So right after the wet impregnation and the drying, we go to a prolonged reduction period to get the final catalyst. This has been developed for gold palladium, and in our lab in Utrecht, Sankar then translated this method also for the synthesis of ruthenium palladium nanoalloys. So what we did is we made a series of catalysts. We made the monometallic gold, the monometallic palladium, the bimetallic gold palladium, the monometallic ruthenium, and the bimetallic ruthenium palladium according to this method. We made the monometallic ones in order to benchmark our bimetallic catalysts in terms of activity. And we also made two additional samples of ruthenium. We made a sample which is called here ruthenium-1. This is a very standard ruthenium and titania catalyst done via a very standard wet impregnation method using ruthenium trichloride as a precursor and including both calcination and reduction steps in the catalyst synthesis. Well, we also made this ruthenium-3. If you think about it, one of the key aspects of modified impregnation is the fact that we need this excess of chloride. But we need this excess of chloride to get intimate mixing between the two types of metals. So if we only have one metal, we don't need intimate mixing, and we can omit the excess of chloride anions, and that's what we did. So we followed the same procedure, except that we didn't use the half molar of HCl, but we did do the direct reduction on the catalyst to get the final state. So that's ruthenium-3, which basically is a modified impregnation method, where we leave out the HCl in the impregnation step. So before I go to the catalytic results, first a bit of structure. We quite extensively characterized these catalysts by using STM-EDX, by using XHAFs, by using XPS, and by using IR spectroscopy after CO adsorption. And these nice STEM pictures were obtained by our collaborators at Lehigh University, Chris Kiley, and they really nicely show that we indeed have control over the size of the nanoparticles. We have quite a uniform distribution with an average particle size of 1.5 nanometers. And then the XLS also confirms this, that this is also representative of the bulk of the sample, and that we have intimate mixing of the two metals in the nanoalloy, and that we have them in roughly more or less the same ratio in there. So this shows that the synthesis method actually works very well. The same goes for ruthenium, also very nice pictures. Again, very small nanoparticles, very narrow in size, about 1.2 nanometers in diameter. And here you can see by the elemental maps that we indeed have very nice mixing of the two elements within the nanoparticle. So this together, the STEM, the X, as well as the XF really establishes these catalysts as random nanoalloys, and we can now use them in catalysis. So what do we see? If we use these catalysts in catalysis, we see two distinct effects of alloy. Both of these catalysts actually perform better in terms of overall performance in the hydrogenation of levulinic acid than their individual counterparts. So if we look at gold and palladium, if we use these catalysts in the levulinic acid hydrogenation, then we basically see hardly any activity. They're lousy catalysts for this particular transformation. If we then use gold palladium, we see a 27-fold increase in activity. We get to decent productivities, and we nicely convert and nicely and cleanly convert levulinic acid to valerolactone. So we see a strong synergistic effect upon mixing gold and palladium, and we actually turn two inactive components into an active nanoalloy. And the reason for that I will come back to later. What do we see with ruthenium? We see similar effects. First, maybe just for benchmarking, there's this wet impregnated ruthenium catalyst that is a standard catalyst. A standard catalyst that gives us standard results. We get a productivity of more or less 5 moles of GVL per gram of metal per hour, and that number is very similar to all the numbers that you find in the table that is listed in the bulk of each review. If we then compare the activities of the monometallic modified impregnation method catalyst and the bimetallic modified impregnation method, then we get similar productivities. This might seem that they're equally active, but we have to keep in mind that what we're plotting here is productivity that is normalized per gram of metal, and basically this means that our bimetallic catalyst is twice as active because the palladium is not doing much. So we have an increase in activity here, but also there's an interesting selectivity difference. And this will, I will come back to that later as well when we look at the XPS and the IR characterization of this material. Because the differences in selectivity become apparent when you let the reaction run for a little bit too long. Of course, you should not overcook your reactions, or you should not use too long reaction times. But basically what it shows here is that for the blue one, the ruthenium palladium, we stay at the GVL level and we do not convert GVL any further. The ruthenium-2 catalyst here is a little bit too active, and it also starts to chew on GVL, and it starts to convert GVL into MTHF, into pentane diol. And this actually has to do with the strength of the interaction between the nanoparticle and the support. What we see is that the SMSI, the strength of the SMSI, is really determines the selectivity and the activity of these catalysts. So what we have is we have sustained activity, at least on the productivity scale that we use here. It's actually a little bit faster than the monometallic catalyst. We've got no overhydrogenation to MTHF or pentane diol, and what I will show you in one of the next slides is that alloy actually greatly improves stability as well, not only activity and selectivity. So what about this third catalyst? So the modified impregnation one, ruthenium-3. If we omit the half a molar of HCl in the synthesis method, what we get is we actually get a monometallic catalyst that is exceptionally active. In this particular case, we have a 10-fold increase of activity compared to our standard ruthenium catalyst. And again, we think this is caused by the fact that we make small nanoparticles where we have a very strong interaction with the titanium support. This makes the ruthenium very active and gives us the high activity in this particular reaction. So it's exceptionally active, it's much more active than the bimetallic catalyst, but there is of course an issue with it. It's a bit unstable, and what we will see is that it sinters a bit and the nanoparticles grow and we lose a little bit of activity for this particular catalyst. So in both cases, for ruthenium palladium and for gold palladium, we see an improvement in activity, we see sustained selectivity, and we also see improvements in stability of the catalyst. So if we reuse the catalyst a couple of times, what we see is that the selectivity is maintained and the activity is maintained. And what is quite important, we don't have any changes to the catalyst material. So what I show you here is the particle size of both the fresh catalyst and the spent catalyst after a number of runs. And what we see is that for the monometallic catalyst, in all cases we see sintering, we see particle growth, whereas for the gold palladium and the ruthenium palladium, we don't see any growth of the particles, actually. And we have a nice stable catalyst that shows us very good activity. It's sort of important that we don't have sintering, but also we don't have any leaching of the metals to the liquid phase. Or at least we have less than 1% of the metal being leached to the liquid phase. So what is causing this? What is causing this improvement in catalytic performance? We did XPS, EXOS, FTIR of the CO absorption, and taken together these techniques provide some insight into the effects of alloy. Of course, it is a very difficult question to answer, and it's very difficult to disentangle the different contributions to the effects of alloying. But what we can say is, at least, that for gold and gold palladium, is that we see electron transfer from palladium to gold, making the palladium cationic. The palladium is diluted in gold, and basically this cationic palladium much more strongly binds to CO, which is an important observation from the IR spectroscopy. And this shows that the palladium is becoming more reactive, and that basically this electron transfer, this electronic modulation of gold, of palladium by gold, is the cause of the increase in activity. For ruthenium palladium, the effect is slightly different. Here, basically, what we're playing with is the strength of the interaction of the nanoparticle with the support. So what we can say from all these different techniques is that we have intimate mixing of the two metals, that we have a modulation of the interaction, the strength of the interaction with the adsorbed carbon monoxide. We see shifts in the binding energy for the different metals, and all these things taken together basically show us that we have reached a bit of an optimum in terms of metal support interaction. So what we have is dilution and isolation of ruthenium by these palladium species, and basically an optimum in interaction between the support and the ruthenium or ruthenium palladium nanoparticles, and this gives us this improved stability and improved selectivity of these catalysts. Of course, much more work needs to be done here, especially computational studies I think are needed to provide further insight into these effects of alloying, but at the first go I think this is, or these are the lines that we're thinking about. Okay, so this all looks really well for titania. We've got stable catalysts, we've got stable monometallic catalysts, we've got stable bimetallic catalysts. But I would also like to show you one example of where all is not well for titania. And this actually came about in our study where we also included ruthenium and zirconia catalyst, and where we start to look at the use of real feeds, or the influence of impurities on catalytic activity. So in this particular part of our studies, what we're looking for are really, we want to look in detail at the relationship between catalyst structure, the influence of catalyst synthesis parameters on catalyst structure, and then the influence on catalyst performance, in particular with respect to deactivation. So we studied the nature of the support, we studied the nature of the solvent, the nature of the synthesis parameters, and we studied the nature of impurities on catalyst deactivation. What we did in the first go is basically we compared different types of supports, carbon, titania, and zirconia supported ruthenium catalyst, and this time we're doing our reactions again in dioxane, right? So fairly mild conditions for the catalyst. The catalysts are prepared by standard wet impregnation techniques, so we use again the ruthenium nitrosyl nitrate as the precursor, and we include both a calcination as well as a reduction step. In this particular project, this is a continuation of the previous work. We're only interested in going to GVL, so we don't want to go beyond the GVL level. So we basically choose some new standard conditions which are slightly milder. We use now reaction temperatures of 150 degrees and 30 bars of hydrogen. Okay, what do we see? If we compare the zirconia, the carbon, and the titania supported catalyst, then we see that they're more or less equally active in this reaction. Titania is lagging behind the other two a bit, but the differences are not too big actually. If we, however, reuse these catalysts, then we start to see a big difference between the two. So what we have here is basically a reuse of the carbon catalyst. So we've done 5 recycle tests, and what we see is that ruthenium on carbon is very stable under these conditions. This has been shown before, that in dioxane or in organic solvents, ruthenium on carbon does not deactivate. The picture is of course very different when you go to water, but it is not something that I want to touch upon today. So ruthenium on carbon shows stable performance in dioxane, and ruthenium on titania doesn't. So ruthenium on titania actually strongly deactivates, which was quite a surprise to us, because we're using fairly mild conditions. We're using dioxane as a solvent, and still we have about 30% loss of activity already after 3 recycle runs. Right, so ruthenium on titania is really quite unstable actually under these conditions. If we then compare this to zirconia, then we see that zirconia actually performs rather well, and even upon 5 times recycling we don't have any loss of activity. Actually we have a little bit of loss of activity after the 5th recycle, but this is due to accumulation of coke on the catalyst, which we can easily burn off, and then we reduce or we restore our activity again. We also run this reaction, of course, at lower conversion levels to show you that we really don't have any deactivation, and upon 5 times reuse we still have the same selectivity and the same activity as at the beginning. So carbon is stable, zirconia is stable, but titania is not. This came as a bit of a surprise to us, and we wondered why this is, because all our previous analyses didn't really show any change in the catalyst structure. Also here, if we look at the metal phase, we don't see any loss of ruthenium to the solvent, we don't see any leaching of ruthenium, we don't see any sintering. We actually have, well, identical particle sizes before and after reaction. But if we look at the support, then we actually do see changes. And the first giveaway was that we see a gradual blackening of the catalyst that we cannot really get rid of even after we try to recalcine or to try to burn off any of the coke that is formed. So the catalyst turns black, and we see that there are significant changes to the support. We see a large drop in BAT, we see an increase in pore volume, and more importantly maybe, if we take the XPS spectra of these spent catalysts, what we see is a very strong reduction of the support. So the top ones here are of the fresh catalyst, the bottom ones are of the spent catalyst after 3 runs, and what you see is that the titania really gets reduced. So we see a strong reduction of the titania 4 to titania 3, and actually the titania 3 to titania 4 ratio increases tenfold. And this was quite a surprise to us, and we see that this is quite systematic. So this increase is quite systematic with the extent of deactivation, so it must be correlated with that, but we don't really understand yet how this influences the catalysis. But one of the conclusions that we can make, at least, is that the titania is not always the preferred catalyst for this reaction, and that there are also some things that can happen to that support as well. So we compare this to ruthenium on zirconia. What we see is that nothing happens to the catalyst. We see no sintering, we see no leaching, no change in particle size. We have got a little bit of coke buildup, about 7-8% after the 5th cycle, but we can easily get rid of that if we burn it off. We see no drop in BAT, and importantly, we see no changes in XPS neither. So, whereas titania shows deactivation, zirconia does not, and for now we kind of have zirconia as our new preferred support for doing these reactions in. Okay. Maybe to take things one step further, so one thing that we are particularly interested in this project is the influence of impurities on the performance of a catalyst. As I said, impurities can be carried over from previous biomass processing steps. For instance, when you do the conversion of biomass to levulinic acid, this is typically catalyzed by a strong mineral acid, and you can have traces of the mineral acid carried over onto the next step. Other impurities can be imagined as well, of course. We can have human precursors that are carried over, we can have small fragments of the lignin that are carried over, etc. And we would like to systematically investigate what the influence of each of these impurities is on catalytic performance. This has been done before, but very limitedly. There's one important study, again by the group of Jumesic, where they show that traces of mineral acid, in this particular case traces of sulfuric acid, greatly influence performance of ruthenium on carbon catalysts. Actually, if you add a little bit of mineral acid to the solution, it will kill the activity of the ruthenium on carbon catalyst. They found a solution against that, so they showed that by alloying or by making the bimetal with rhenium, the catalyst will show improved stability against these traces of mineral acids. Actually, they show that you can keep producing GVL even in the presence of sulfuric acid, but the activity of the catalyst that you have, the activity of the ruthenium-rhenium catalyst, is lower than the activity of the ruthenium on carbon catalyst without the addition of sulfuric acid. So improved stability comes at the expense of a bit of activity in this particular case. Well, we also studied the effect of sulfuric acid on our catalyst, and we get the same effect. So if we just take ruthenium on carbon, but this also goes for ruthenium on titanium, we see that it's very rapidly deactivated in the presence of sulfuric acid. Already at 0.18% of sulfuric acid, we completely kill the activity of the catalyst. Quite to our surprise, we saw that ruthenium on zirconia shows some nice behavior in the presence of sulfuric acid. So what we did is we made some bimetallic catalysts, just like the group of Jumesic did. And we also tested our ruthenium on zirconia in the presence of sulfuric acid. So these are reactions run at 0.1 weight %, so that is a percentage that almost fully kills the activity of the ruthenium on carbon catalyst. But here on the top left corner you can see that the ruthenium zirconia catalyst is actually not so much affected. It doesn't really care about the presence of the sulfuric acid. We did some more studies, and what we see is that basically what the zirconia does, it acts like a scavenger, and it has a certain absorption capacity. And if we treat our zirconia well, then actually we can maintain our activity also upon multiple recycles. So if we clean the catalyst in between runs, and we clean the catalyst by washing it with hot water, we can basically maintain the activity of the ruthenium zirconia catalyst also in the presence of sulfuric acid. And we keep also our high activity of the ruthenium zirconia catalyst. So we thought that this is quite interesting, and this is something that we're exploring further at the moment. Okay, for the last bit I would like to shift gears a bit, and I would like to go to deeper hydrogenation reactions. So now we let go of the conversion of levulinic acid to valerolactone, but we try to go one step further and we try to go down to the pentanoic acid level. And what I will show you here is that again by having a careful catalyst synthesis, we can basically optimize the properties of the catalyst and selectively get also to this pentanoic acid level. Well, why make pentanoic acid? Well, there are a few nice examples of the nice things that you can do with pentanoic acid. One example by the group of Blanche from Shell, already published a couple of years ago now, where they show that you can go all the way in consecutive steps from levulinic acid to valeric acid or pentanoic acid esters, and these pentanoic acid esters are very nice biofuels. Jurassic also showed that there are nice things to do with pentanoic and pentenoic acid, converting it via different kinds of chemistry to all different kinds of fuel ranges. The key step is here, going from gamma-valerolactone to levulinic acid, or sorry, going from gamma-valerolactone to pentanoic acid. And what both the large group and the Jurassic group use for this is a bifunctional catalyst where you have a metal hydrogenation function as well as a strong acid, and the strong acid is required to ring open the GVL to pentanoic acid, and then the steps after that, hydrogenation of pentanoic acid is actually quite straightforward. Well, given our initial hit, in our first screening we already saw pentanoic acid directly formed over our ruthenium zeolite supported catalyst, and we thought, well, can we optimize that and can we do this in one pot without intermediate isolation of gamma-valerolactone? So this is what I would like to focus on here. So what you see is that both beta and ZSM5 give us some pentanoic acid. Beta gives us less pentanoic acid than ZSM5. I'll show you in a second why this is. And what we did is we basically tried to optimize the yield through variation in catalyst synthesis. We played with the synthesis quite a lot until we got this under control. And as always, we are very interested in catalyst deactivation, and we exposed these ruthenium zeolite catalysts to our most stringent conditions. We actually run them in ethyl-hexanoic acid, and we wanted to see what would happen under these conditions. I will very shortly touch upon the deactivation before I go to the optimization of the catalyst. What we see is that also in EHA we get pentanoic acid, but we get less pentanoic acid as we would get in dioxane. This is of course again because of competitive absorption, but also because of deactivation of the catalyst. So you have to keep in mind is that we're boiling the zeolite in this acid for 10 hours, so these are very stringent conditions for the zeolite, and we can expect some deillumination to occur. H-beta also gives us pentanoic acid, but it gives us less pentanoic acid than ZSM5. But if we actually look at low conversions, we see that beta gives us more pentanoic acid than ZSM5. So the initial activity of beta is higher, but at the end of the run, we get less pentanoic acid, which means that beta deactivates faster than ZSM5 does. Well, there are all kinds of things going on in terms of deactivation. We've got some carbon deposition. There are quite some interesting things to say about this carbon deposition, but I won't touch upon that today. I would like to focus on the extent of deillumination that happens with these zeolite catalysts. So we did IR studies after peer unit absorption, and we did some 1D and 3D or 3Q mass aluminum NMR studies to identify what happens to the acid sites in these catalysts after reaction in ethyl-hexanoic acid. What we see here is that actually the amount of Brunzett acid sites and Lewis acid sites in ZSM5 doesn't change too much. We see some shifting of the peaks, which are quite interesting, I think, which show us some interaction between the framework aluminum sites and the extra framework aluminum sites. The story is quite different for H-beta, though. There we see an enormous drop in Brunzett acid sites, and we also see quite a large drop in Lewis acid sites. We further quantified this by the aluminum NMR studies. We actually fitted, or our collaborator Rens van Eck in Nijmegen University fitted the 3Q mass data, and this allowed us to simulate the 1D NMR spectra again and to get some insight into the speciation of aluminum and the changes in speciation. And what we saw was the following. We see that the extent of the illumination is actually fairly limited for HZSM5, and we see that the extent of the illumination for H-beta is quite severe. So under these forcing conditions, we lose about 40% of our aluminum, about 40% of our strong acid sites. This is quite well in line with what is known for on-purpose deillumination as a pretreatment method for zeolites. I mean, beta is more easily deilluminated than HZSM5, but I think this is also something that we need to keep in mind when we're doing our levulinic acid conversions, because we're also exposing our zeolites or our systems to this acid for a prolonged amount of time. So we see difference in speciation, but the most important thing I think here is that the extent of acid loss really determines the deactivation of the catalyst. So this showed us that ZSM5 is actually preferred over beta, even though beta shows initially higher activity, and we continued with HZSM5 for our catalyst optimization studies. So what we did, we played a bit with the ruthenium type, we played a bit with the zeolite type, and we played a bit with the silicon to aluminum ratio. These were our old conditions, wet impregnation with this particular precursor, and we had calcination and reduction steps. We changed this then, and we made a series of catalysts where we basically omitted the calcination step. That's the first important thing. We changed the ruthenium precursor to these two here, and we changed the zeolite precursor to the protonated form and the one in the ammonia form. And the goal here is basically the retention of strong acid sites and to improve the proximity between the hydrogenation function and the acid function of the catalyst. So we made this whole series of catalysts, and this is what we got. If we compare the different precursors with each other, so change of zeolite precursor, change of ruthenium precursor, then we can see that there's a large influence on catalytic activity. The red line is the one that we want to follow, that is the PA production line, and basically when we use the hexammonium trichloride form of ruthenium and when we use the ammonium form of the zeolite, we basically get our best PA activity. So what is the reason for this? Well, what we can see is that basically what we do is we do two things. By variation of the catalyst synthesis, we retain the most of our strong acid sites in our optimal case, and also we have the best proximity, the most ruthenium actually located inside of the pores of the zeolite, and the best proximity between the two catalytic functions. Okay. If we then optimize the conditions a bit, then we can actually push the yield of PA to 91% and get very good productivities also for this particular direct conversion. Wrap up. What happens to the catalyst? Keep in mind that now we're doing our reactions in dioxane. These are quite mild conditions. We don't have severe deillumination. And actually what happens is that if we reuse our catalyst, we see a drop in activity. But the drop in activity in this particular case is not due to deillumination, it's actually loss of acid sites to coking. So if we simply regenerate the catalyst by a coke burn-off, then we almost completely regenerate the activity of the catalyst and we can use it again and we can go back to our old levels of activity. Okay, that brings me to the end of my talk. I hope I've showed you that the choice of support, the choice of catalyst synthesis, the choice of solvent is very important. It greatly influences performance and stability. We've made some nice bimetallic catalysts for the La to GVL reaction. We've made some nice zeolite-supported catalysts for the La to PA reaction. And I think something that is required now and something that we should focus on as a field is more stability studies, more insight into the modes of deactivation, and more insight into the study of impurities that we can expect in real fields that we in the end need to deal with. Finally, I would like to acknowledge these people. I would like to acknowledge my co-workers at Utrecht University, our collaborators who have contributed with various analytical techniques, and I would like to acknowledge Catch Bio for funding and you for your kind attention. Thank you.
We have time for a quick question.
Thank you, Pieter. The sulfuric acid poisoning that you report, do you understand it?
No?
It's not the poisoning, but the lack of poisoning with...
Yeah, so we've done a lot of control reactions, so using sodium sulfate, combinations of sulfuric acid, sodium sulfate, using different physical mixtures, etc. But we don't completely understand it yet, so we're doing quite a lot of characterizations now on the spent catalyst to see where the sulfur goes. We see very specific trends in when we open the pot if we smell sulfuric H2S or not. We understand it a bit, but not enough to give you an answer right now.
Too bad.
Okay, in the interest of time, I'm afraid we have to move on, but please join me in thanking Pieter again for a very nice keynote lecture.